Hi everyone. Today's class is slightly connected to one of our previous classes, that is boiling point diagrams. So here I am going to discuss about Raoult's law. The calculation and generation of boiling point diagrams are based on Raoult's law. A French chemist, Francois Marie Raoult, in 1887 proposed the Raoult's law. Francois Marie Raoult. In the year 1887 proposed Raoult's law. It states that at any particular constant temperature, the partial pressure of one component of a mixture is equal to the mole fraction of that component multiplied by its vapor pressure in the pure state at the same temperature. So it has one more definition which states that the vapor pressure of a solution is equal to the sum of the vapor pressures of each volatile component if it were multiplied by the mole fraction of that component in the solution. The vapor pressure of a solution is equal to the sum of the vapor pressures of each volatile component if it were purely multiplied by the mole fraction of that component in the solution. So the partial pressure of the component varies linearly from 0 to maximum as the mole fraction varies from 0 to unity. So we know that mole fraction can only range from 0 to unity. So as the mole fraction ranges from 0 to unity, the partial pressure of each component varies linearly from 0 to the maximum value. So we can represent mathematically the equation for Raoult's law. P pressure of solution is equal to the mole fraction of solvent, one of the component XA, let it be solvent, and pressure of that solvent in its pure state. Pressure of that particular solvent in its pure state, where P solution, it is the vapor pressure of the solution, and X solvent, it is the mole fraction of the solvent, and P naught solvent, it is the vapor pressure of the pure solvent. So as per our definition, partial pressure of the vapor pressure of the solution is equal to the partial vapor pressure of the pure solvent multiplied by its mole fraction in its pure state. So as we know that a solution is composed of solvent and a solute, where the solvent will be in higher quantity and solute will be in lesser quantity. So when we are mixing a solute and a solvent, and in a tight container, there is a chance of evaporation of solute particles and solvent particles, and they will be in dynamic equilibrium with that of the liquid solution here. So solvent as well as solute particles will get evaporated from the surface of this liquid in a chamber, and it will be in dynamic equilibrium with that of the solution. So what is the pressure exerted by component A or the solvent, and what is the pressure exerted by component B or the solute, that can be determined by this Raoult's law. So therefore the validity of Raoult's law holds only over a very short range of compositions, because Raoult's law, it is mainly applicable only for ideal solutions. So it is fit only for ideal solutions which are hard to find, very hard to find. And ideal solution, we know that ideal solution, it's a solvent solute interaction is same as that of a solvent interaction and solute interaction. So in case of a solution, A and B are combining to form a solution. We know that suppose A is solvent and B is the solute here. We know that A must have interaction with that of B. the solvent should have interaction with that of the solute. So there will be number of A, B interactions in the solution. So similarly, when we are taking A alone, A interaction will be possible. The interaction between the solvent molecules are possible. Interaction between the solute molecules are also possible. So this interaction and this interaction must be same as that of the A and B interaction, which is very hard to find. And if it is same, the interaction between the solvent and solute molecules are, if it is same as that of the interaction between solvent and the solute interaction, then we can call it as a solution as ideal solution. So Raoult's law, it is mainly applicable for non-aqueous solutions. So that is one of the advantages with this Raoult's law, and it is mainly for the ideal solution, so which is very hard to find. So this is we can call it as, this is one of the limitations of Raoult's law. So when we talk about Raoult's law, we have to speak about the relative volatility also. Relative volatility can be expressed as alpha AB, two components A and B, YA divided by that of XA divided by YB XB, where Y is the mole fraction of component in vapor phase and X is the mole fraction of component in liquid phase. So mole fraction, we know that it ranges from 0 to 1. Maximum will be 1 and the minimum will be 0, even in case of A and B. And the total mole fraction XA plus XB will be equal to 1. Okay, so this is the equation to find out. And the equation to find out the mole fraction of XA is equal to number of moles of A divided by total number of moles. N A divided by Na plus Nb. Na stands for number of moles of A, Nb stands for number of moles of B. So mole fraction of A, the component A, is equal to the number of moles of A divided by that of total number of moles. So in case of binary system, YB is equal to 1 minus YA. So if there are only two components, YB is equal to 1 minus YA, which comes from this equation. Okay, and XB is equal to 1 minus XA, because XA plus XB is equal to 1. Therefore, if the liquid phase obeys Raoult's law and the vapor phase obeys Dalton's law, we can get alpha is equal to PA divided by PB. So hope you understand the concept of Raoult's law and the equations regarding Raoult's law. Thank you.